The oceans of prehistoric Earth were home to creatures that seem impossible. Millions of years ago, enormous predators lived in the seas. Some had very long jaws, and others had extremely sharp teeth. Some could swallow large prey whole, while others lived in deep waters, hunting quietly and efficiently. 200 million years ago, the seas contained animals that were extremely large and very fast. Fossils show that these creatures were strong, dangerous, and highly effective hunters. They lived in ways that are difficult to imagine today. Adaptations Megalodon was one of the most enormous and fearsome sharks to ever live in Earth's oceans. This giant predator swam through the seas from about 23 million years ago to around 3.6 million years ago, a vast stretch of time that covered parts of what scientists call the Miocene and Pliocene periods. For a long time, people believed this massive shark was closely related to the modern great white shark, placing it in the same family. However, later research showed that it actually belonged to a completely different and now extinct family, meaning its line had split away from the ancestors of the great white much earlier than once thought. Even though it is often described as one of the most powerful predators in history, much of what we know about this giant comes from incomplete fossil remains, especially its famous teeth. Because of this, scientists are still not completely certain what its full body looked like. Some experts believe it had a thick, heavy body built for strength, while others think it may have been longer and more streamlined, like many modern sharks. Estimates of its size vary widely, with some suggesting it could grow as long as between 14 and 24 meters, while a more common estimate for most individuals is around 10 meters. What is certain, however, is that its teeth were incredibly strong and thick, perfectly designed for gripping prey and crushing bone. Its jaws were equally terrifying, capable of producing a bite force so powerful that it could easily shatter the bodies of large animals. This giant shark played a major role in shaping life in the oceans. Fossil evidence shows that it lived in seas all around the world, making it a truly global predator. It likely hunted some of the largest animals of its time, including whales, seals, and sea turtles. Younger individuals preferred warmer coastal waters, where they fed on smaller prey like fish and young whales. Unlike the great white shark, which often attacks from below and targets softer parts of its prey, this massive hunter likely used its immense strength to bite directly into the chest area, breaking through ribs and reaching vital organs like the heart and lungs. However, this powerful predator did not rule the oceans without challenges. It faced competition from other large hunters, including ancient whale-eating creatures like Liopluridon and other powerful relatives of modern sperm whales, as well as early forms of killer whales such as Orcanis. Over time, major changes in the Earth's climate began to reshape the oceans. As the planet cooled and ice ages began, sea levels dropped and many of the warm coastal areas that served as safe nursery grounds disappeared. At the same time, many of the large whales it depended on for food either became less common or moved toward colder regions near the poles. With less food and fewer suitable habitats, this once dominant predator slowly declined and eventually disappeared. Interestingly, its extinction happened during a time when some whales were actually growing larger, suggesting a major shift in the balance of ocean life. Long before scientists understood what these giant teeth truly were, humans had already discovered and used them. Ancient cultures in the Americas valued these large, sharp fossils and turned them into tools, weapons, jewelry, and ceremonial objects. Some societies used them mainly for rituals rather than everyday purposes. In parts of North America, indigenous groups even mined these teeth and traded them over long distances. In ancient times, people did not realize these objects came from sharks. The Roman writer Pliny the Elder described them as stones that looked like human tongues and believed they had fallen from the sky during lunar eclipses, calling them tongue stones. Later traditions in places like Malta claimed they were the petrified tongues of snakes turned to stone by Paul the Apostle. People believed these stones had magical powers, especially the ability to protect against poison. During the Middle Ages and the Renaissance, they became highly valued among nobles, who used them as protective charms or even placed them in cups and dishes, believing they could neutralize poison. It was not until the scientific revolution that people began to question these ideas. In the 16th and 17th centuries, scholars such as Fabio Colonna argued that these tongue stones were actually fossilized shark teeth. He compared them directly with the teeth of modern sharks and pointed out their clear similarities. Later, scientists like Niels Stenson strengthened this idea by carefully studying shark anatomy and fossils. Through observations and experiments, they showed that these objects were once part of real animals and had been preserved in rock over long periods of time. Stenson also helped explain how such fossils could be found far from the sea, suggesting that areas now on land were once covered by oceans and later lifted up by changes in the Earth's surface. Eventually, the giant shark was given a formal scientific name by the Swiss scientist Louis Agassiz in the 19th century. He first grouped it with sharks that seemed similar, but later adjusted its classification as scientists learned more. Its name, meaning big tooth, perfectly reflects the most famous and best-preserved part of this incredible creature. The story of when the giant shark known as Otodus Megalodon first appeared is not as clear as it might seem. Some of the oldest fossils that scientists have found come from a time called the Late Oligocene, which was around 28 million years ago. But not everyone agrees on this. Other researchers believe this massive predator may have shown up much later, perhaps around 16 million years ago. Because of this, the true beginning of Megalodon's reign in the oceans remains a subject of debate, with different scientists interpreting the evidence in different ways. Its disappearance is also surrounded by uncertainty. For a long time, it was believed that Megalodon went extinct near the end of the Pliocene epoch, roughly 2.6 million years ago. Some fossil teeth have been claimed to be younger than that, suggesting the shark might have survived longer, even into the Pleistocene. However, these claims are widely doubted, as the evidence is not considered reliable. A more recent study carried out in 2019 suggested that Megalodon may have actually vanished earlier than previously thought, around 3.6 million years ago. This means the great shark's final chapter may have closed sooner than scientists once believed. When it comes to classifying Megalodon, the story becomes even more complex. Today, most scientists place it in a group of ancient sharks called the Odontocetidae family, within the genus Otodus. This is different from older ideas, where Megalodon was grouped together with the modern great white shark in the genus Carcharodon. That earlier classification was mainly based on how similar their teeth looked. At first glance, the sharp triangular teeth of Megalodon seem very much like those of the great white shark. But scientists now believe this similarity is not because they are closely related. Instead, it is likely the result of a process called convergent evolution, where different animals develop similar features because they live in similar environments and hunt in similar ways. In fact, research suggests that the great white shark is more closely related to another extinct shark known as Cosmopolitodus hastalis than it is to Megalodon. The teeth of these two sharks share more detailed similarities, which points to a closer family connection. They are also linked to modern mako sharks from the genus Ichthyosaurus, and scientists estimate that their shared ancestor lived around 4 million years ago. Still, not everyone agrees with this newer view. Some researchers argue that the differences between Megalodon and great white teeth are very small and not enough to separate them so clearly. The evolutionary history of Megalodon and its relatives tells a long and fascinating story of gradual change. Scientists have identified a group of related sharks that seem to form a lineage leading up to Megalodon. Over time, their teeth became more advanced, developing sharper edges, wider crowns, and a more triangular shape. Small side points on the teeth, known as lateral cusps, slowly disappeared. This transformation likely reflects a major shift in how these sharks hunted. Earlier species may have grabbed and torn their prey, but later forms, including Megalodon, were better suited for slicing through flesh. This change suggests that their diet may have shifted from fish to larger animals such as whales. This transformation did not happen quickly. The loss of those side cusps alone took about 12 million years, showing just how slow and steady evolution can be. Different scientists have proposed different ways of organizing these species into groups. Some believe they all belong to a single line within the genus Otodus, while others have separated them into a group called Carcharocles. There is even a view that several of these species were actually just one species slowly changing over time, a concept known as a chronospecies. Because of these debates, Megalodon's scientific name has changed more than once. Some researchers argue that it should properly be called Otodus megalodon, placing it firmly within the Otodus lineage. Others have suggested different names and groupings over the years, including the use of a subgenus called Megacelicus. New fossil discoveries have continued to reshape these ideas. For example, the discovery of another ancient shark group led scientists to rethink how all these sharks are related, suggesting that combining them into one larger group might better reflect their true evolutionary history. As for what Megalodon actually looked like, scientists can only make educated guesses, since no complete skeleton has ever been found. One common idea is that it looked similar to the great white shark, but much larger and more powerfully built. In this view, it would have had a broad, strong body, a wide jaw, and thick fins designed to support its enormous size. Its eyes may have been relatively small and set deep into its head. Another possibility is that it looked more like gentle giants such as the whale shark or the basking shark, at least in body shape. In this version, Megalodon would have had a long, streamlined body with a crescent-shaped tail built for moving efficiently through the water. This kind of design is common among very large ocean animals, including whales and fast-swimming fish like tuna, because it helps reduce drag and conserve energy. Recent research has added even more detail to this picture. Studies published in 2024 and 2025 suggest that Megalodon may have had a more elongated body than earlier scientists thought. By comparing parts of its skull and tail with those of living sharks, researchers concluded that it might have been longer and more streamlined than previous estimates suggested. In 2023, scientists also examined tiny fossilized scales from Megalodon. These scales were extremely small, measuring only a fraction of a millimeter, and had special ridges on their surface. By studying the spacing of these ridges and comparing them with modern sharks, researchers were able to estimate how fast Megalodon could swim. Their findings suggest that, although it was not built for constant high speed, it may have been able to produce sudden bursts of power when chasing prey. They also found evidence that Megalodon may have been regionally warm-blooded, meaning parts of its body could stay warmer than the surrounding water, giving it an advantage in hunting. Because the remains of Otodus megalodon are so incomplete and broken apart, scientists have struggled for many years to agree on just how big this ancient shark really was. Most of what we know comes only from fossilized teeth and a few pieces of its backbone, and that makes things difficult. Without a full skeleton, researchers have had to make careful guesses, often comparing these fossils to the body of the modern great white shark, which is considered the closest living example. By studying how the teeth and bones of the great white match its overall size, scientists try to scale up those relationships to imagine the full body of Megalodon. Even with these methods, the estimates vary widely. Different scientists, using different approaches and ideas about how the shark's body was shaped, have suggested that Megalodon could have reached lengths anywhere from about 14 meters to more than 24 meters. Some earlier research proposed that adult males might have been between about 10 and 14 meters long, while females were likely even larger, possibly growing to around 13 to 17 meters. In terms of weight, these massive animals may have ranged from roughly 12 to nearly 60 metric tons, with females again being heavier on average. A later study, which examined more than 500 fossil teeth collected from many places and time periods, suggested that a typical adult megalodon may have been closer to about 10 meters long. However, the full range of sizes, from very young individuals to the largest adults, may have stretched from just over 2 meters all the way up to nearly 18 meters. For comparison, even a very large great white shark today usually grows to about 6 meters, though a few reports claim slightly larger sizes. The biggest fish alive today, the whale shark, can reach lengths of around 19 meters, showing just how enormous Megalodon may have been in comparison to modern ocean life. It is also possible that not all Megalodon were the same size. Different populations living in different parts of the world may have grown larger or smaller depending on their environment, the climate, and the kind of prey available to them. Even with all the uncertainty, scientists generally agree that Megalodon was the largest hunting shark that has ever existed. In more recent years, researchers have tried to build more detailed models of this giant. In 2020, a team led by scientists created a two-dimensional reconstruction based on the proportions of living sharks in the same family. According to this model, a Megalodon about 16 meters long would have had a head nearly 5 meters in length, tall gill openings, a large dorsal fin rising more than 1.5 meters, long pectoral fins stretching over 3 meters, and a powerful tail almost 4 meters tall. Then, in 2022, the same group produced a three-dimensional version of this model. This new reconstruction suggested that a 16-meter megalodon could have weighed over 60 metric tons, making it even heavier than earlier estimates. This new reconstruction suggested that a 16-meter megalodon could have weighed over 60 metric tons, making it even heavier than earlier estimates. To support their calculations, they studied a fossil backbone from Belgium that likely belonged to an individual around 46 years old. Based on this and other data, they estimated that such a giant would have needed an astonishing amount of energy each day, nearly 100,000 calories, which is about 20 times more than what an adult great white shark requires. Interestingly, this newer research also suggested that Megalodon may have had a longer, more stretched-out body than scientists once believed. Instead of being shaped exactly like a great white, it might have been more elongated. Later studies supported this idea, estimating a similar length of a little over 16 meters, but with a lower body weight, somewhere between about 27 and 34 metric tons. This shows that even today, scientists are still refining their understanding of this ancient predator. When it comes to movement, researchers have tried to estimate how fast Megalodon could swim. One study suggested that it may have cruised through the ocean at around 18 kilometers per hour, which is similar to large modern marine animals like the fin whale. Another study later translated this into a different way of measuring speed, showing that while its absolute speed was quite fast, its speed relative to its body size was actually slower than smaller sharks. This makes sense, as larger animals often move more slowly relative to their size, even if they cover great distances. The enormous size of Megalodon likely came from several factors working together. Warmer climates in the past, along with an abundance of large prey such as whales, would have supported the growth of such a massive predator. There is also strong evidence that Megalodon may not have been entirely cold-blooded like most sharks. Instead, it may have had a form of regional warm-bloodedness, allowing parts of its body to stay warmer than the surrounding water. This would have increased its energy use, strength, and swimming ability, making it a more powerful hunter. However, some scientists have even suggested that its great size may have begun before birth. In a process seen in some modern sharks, embryos inside the mother can consume their smaller siblings, allowing the surviving young to grow larger and stronger before they are even born. This intense competition in the womb could have pushed the evolution of larger body sizes over time, as mothers needed to grow bigger to support such demanding offspring. Males, in turn, would also need to grow larger to successfully mate with these giant females, continuing the cycle that helped produce one of the most powerful predators the oceans have ever known. Scientists have spent many years trying to figure out just how large the giant shark known as Otodus megalodon really was, and their ideas have changed again and again as new methods and fossils were studied. In the year 1909, Bashford Dean created one of the first full jaw reconstructions of this massive predator, which was displayed at the American Museum of Natural History. Based on the size of that jaw, it was suggested that Megalodon could have grown to nearly 30 meters in length. This sounded astonishing, but later it became clear that the estimate was too high. The cartilage in the reconstructed jaws had been made too large, which caused the overall size to be exaggerated. Decades later, in the early 1970s, Johnny Randall took a different and more careful approach. Instead of rebuilding the whole jaw, he measured the enamel height of the teeth, which is the vertical distance from the base of the enamel to the tip of the tooth. Using this method, he estimated a much smaller maximum length of about 13 meters. However, this method also had its weakness, because tooth enamel does not always grow in direct proportion to the total body size of the shark. By the mid-1990s, researchers like Patrick J. Shembry and Stephen Papson suggested that Megalodon may have reached lengths closer to 24 to 25 meters. This showed that scientists were still trying to refine their understanding, moving between smaller and larger estimates as new ideas were tested. In the year 1996, a team of researchers led by Michael D. Gottfried, along with Leonard Campagno and S. Curtis Bowman, introduced a more mathematical method. They studied the relationship between the size of teeth and the total body length of the modern great white shark. By comparing this relationship to Megalodon teeth, they estimated a length of about 15.9 meters from a tooth measuring about 16.8 centimeters. They also compared this with large female great white sharks. A 6-meter female gave an estimate of about 16.8 meters for Megalodon, while a larger 7.1-meter individual suggested a possible maximum of around 20.2 meters. In the early 2000s, Clifford Jeremiah proposed yet another idea. He believed that the width of the tooth root could be used to estimate the total body length. According to his method, each centimeter of root width corresponded to about 1.4 meters of shark length. Using a tooth with a root width of about 12 centimeters, he estimated a total length of around 16.5 meters. At the same time, in the year 2002, Kenshu Shimada introduced a new method based on the height of the tooth crown. He carefully studied the anatomy of several specimens and created a model that could estimate body length from almost any tooth. He pointed out that earlier methods were less reliable because they did not fully account for differences between Megalodon and modern sharks. Using his approach, one well-known tooth suggested a total length of about 15 meters, while another fossil from the Gatun Formation gave an estimate of about 17.9 meters. Years later, in the late 20-teens, Shimada revisited his work and warned that not all teeth should be used for size estimates. He explained that it is often difficult to know exactly where a loose tooth came from in the jaw. Focusing only on the most reliable teeth, he estimated a maximum length of about 14.2 meters from one specimen. Another famous tooth, originally thought to be 16.8 centimeters tall, was remeasured and found to be slightly smaller at 16.2 centimeters, giving an updated estimate of about 15.3 meters. In the early 2020s, a new method was introduced by Victor J. Perez, Ronnie M. Leader, and Teddy Badal. Instead of focusing on a single tooth, they used the combined width of multiple tooth crowns from a full set of teeth. They discovered that earlier methods could give very different results, even for teeth from the same shark, with possible errors of up to 9 meters. Using a large tooth with a crown width of about 13.3 centimeters, they estimated a maximum body length of around 20 meters, with an uncertainty of about 3.5 meters. This estimate was later supported by other researchers. By the mid-2020s, Shimada and his colleagues suggested an even more surprising idea. They proposed that Megalodon may have had a more elongated body than previously thought. Based on this, they estimated a possible maximum length of about 24.3 meters. A shark of this size could have weighed between about 83.6 and 104.7 metric tons and may have cruised through the ocean at speeds between about 2.1 and 3.5 kilometers per hour. Fossil discoveries have also added to this picture. Some extremely large teeth have been found, including one owned by Gordon Hubble, which measures about 18.4 centimeters in height. Another impressive reconstruction by Vito Bertucci includes a jaw over 2.7 meters wide, with a tooth said to be over 18 centimeters tall. The teeth of Megalodon are the most common fossils we have, and they reveal a great deal about the shark. These teeth are large, triangular, and incredibly strong, with fine serrations along the edges that would have helped slice through flesh and even bone. They were arranged in multiple rows, with more than 250 teeth in total. The shark likely had 4 different types of teeth, each with a specific role, and its jaws may have stretched to about 2 meters across. It could probably open its mouth to a very wide angle, possibly as much as 75 degrees or even more. Studies of bite force show just how powerful this predator was. In experiments led by Stephen Rowe, scientists estimated that Megalodon could bite with a force between about 108,000 and 182,000 newtons. This is far greater than the bite of the modern great white shark and even stronger than that of the ancient armored fish Dunkleosteus. When the shark shook its head from side to side while feeding, the force would have been even more destructive. More recent studies using advanced computer modeling, carried out by Antonio Balel and Humberto Ferron, showed that Megalodon teeth experienced especially high stress when forces were applied from the side. This suggests that the shape of the teeth may not have been designed only for a specific diet, but could also be linked to the shark's enormous size and growth patterns. Because sharks have skeletons made of cartilage instead of bone, most of Megalodon's body did not fossilize well. What remains are mainly teeth, parts of the spine, and fossilized droppings known as coprolites. Even so, these pieces allow scientists to imagine its body. It likely had a stronger, heavier jaw and a more solid skull than the modern great white shark, along with large, powerful fins suited to its massive size. Some rare discoveries of fossil vertebrae give further clues. One important find from Antwerp Basin in the early 20th century included 150 vertebrae, ranging from small to very large in diameter. Another discovery from Graham Formation included 20 vertebrae, some reaching over 20 centimeters across. These findings suggest that Megalodon may have had more than 200 vertebrae in its spine, making it one of the most massive sharks to have ever lived. Complete sets of teeth have also been found, such as one discovered in Saitama and another from the Yorktown Formation. These discoveries helped scientists rebuild the shark's dental layout and better understand how its mouth functioned. Although most sharks will eat whatever they can find, Otodus megalodon was something far more formidable. Its enormous body, its ability to swim quickly, and its crushingly powerful jaws made it one of the most dominant hunters ever to exist in the oceans. This was not just a large shark, it was a true apex predator, sitting at the very top of the food chain and capable of feeding on a wide variety of animals. Scientists have been able to understand its diet in surprising ways. By studying chemical clues such as calcium and nitrogen isotopes preserved in fossils, researchers discovered that Megalodon fed at a much higher level in the food chain than even the fearsome great white shark. In simple terms, this means it hunted bigger and more powerful prey, placing it among the most dangerous predators the planet has ever seen. Close examination of its fossilized teeth reveals even more. Tiny scratches and wear patterns show that Megalodon was not picky. It ate almost anything it could overpower. Its menu likely included shellfish and other invertebrates, large fish, marine reptiles, and especially marine mammals. Fossils provide direct and dramatic evidence of its feeding habits. Many ancient whale bones have been found with deep cuts and gouges that match the shape of Megalodon's teeth. In some cases, the teeth themselves have been discovered lying right beside the remains of their prey, leaving little doubt about what happened. Megalodon regularly hunted dolphins, small whales, and even massive species such as sperm whales and early baleen whales. It also preyed on seals, sea cows, and sea turtles. It was an opportunistic hunter, meaning it would take advantage of any chance to attack, whether that meant chasing fast-moving fish or ambushing large marine mammals. Its hunting style was both powerful and strategic. Like modern great white sharks, it likely used clever attack techniques rather than relying on brute force alone. However, there was a key difference. While great whites often attack the soft underside of their prey, Megalodon appears to have aimed for vital organs such as the heart and lungs. Its thick, serrated teeth were built to cut through bone, and fossil evidence shows heavy damage to ribs and other strong skeletal parts of whales. This suggests it attacked with incredible force, going straight for the most lethal strike. In some cases, the evidence tells an even more dramatic story. Fossils of smaller whales show signs that they were rammed from below with tremendous power before being killed. Their bones display crushing fractures, indicating that the shark struck them like a living battering ram before finishing them off. There are also signs that Megalodon used different tactics for different prey. For example, a fossil tooth from a prehistoric sperm whale shows bite marks that suggest the shark attacked the head, possibly trying to crush the jaw in a single devastating bite. The position of these marks suggests this was an active hunt, not scavenging, and it highlights just how powerful its bite must have been. As time passed and larger whales evolved, Megalodon seems to have adapted its methods. Fossilized bones from the later period show bite marks on whale flippers and tails. This suggests the shark may have first immobilized its prey, crippling it so it could not swim, before delivering the final killing bite. This strategy would have been especially useful against massive whales. Young and adult megalodons likely lived very different lives. Juveniles preferred coastal areas filled with smaller prey like fish, turtles, and small whales. Adults, on the other hand, moved into deeper offshore waters where they could hunt much larger animals. This shift in diet as they grew helped reduce competition between young and mature sharks. Growth in Megalodon was relatively fast, but it took a long time to reach full maturity. Studies suggest that individuals may have taken around 25 years to fully grow, and some may have lived for close to a century. They were already quite large at birth, measuring several meters long, but even so, young megalodons were vulnerable. Other large sharks, such as the great hammerhead shark, could prey on them. Like many modern sharks, Megalodon likely gave birth to live young in nursery areas. Warm, shallow coastal regions, rich in food, and relatively safe from larger predators. Fossil evidence from places such as Panama, North America, and parts of Europe suggests these nurseries were spread across the world. In fact, Megalodon lived almost everywhere. Its fossils have been found across multiple continents, showing that it had a global distribution. It preferred warm and moderate waters, but could tolerate a wide range of temperatures, possibly because it could maintain a body temperature slightly higher than the surrounding water. This ability gave it an advantage, allowing it to hunt in environments that would challenge many other sharks. Despite its dominance, Megalodon lived in a highly competitive world. Other powerful predators shared the oceans with it, including giant predatory whales like Liopluridon. These massive hunters likely competed with Megalodon for the same prey, creating constant pressure in the ecosystem. Over time, the world began to change. The oceans cooled, sea levels shifted, and important waterways closed. These changes affected ocean currents and reduced the availability of food. Many smaller whale species, which may have been a key food source for Megalodon, began to disappear. At the same time, new predators and competitors emerged, including early relatives of modern killer whales. As food became scarcer and habitats changed, Megalodon faced increasing challenges. Its large size, once a great advantage, may have become a weakness, as it required enormous amounts of food to survive. Gradually, its numbers declined. Eventually, around 3.5 million years ago, Megalodon vanished completely. Its extinction reshaped the oceans. With this giant predator gone, other species, like the great white shark, were able to expand and thrive. Meanwhile, whales began to grow larger, possibly because the threat from such a massive hunter had disappeared. Liopluridon was a powerful and fearsome sea reptile that lived millions of years ago during a time when the oceans were filled with strange and dangerous creatures. It belonged to a group of marine reptiles known as plesiosaurs, and it existed from the Colovian stage of the Middle Jurassic period to the Kimmeridgian stage of the Late Jurassic period, which is roughly from about 166 million years ago to about 155 million years ago. The main and most widely accepted species is called Liopluridon ferox, and many scientists believe this is the only truly valid species in the group. Another name, Liopluridon pachydiris, has been suggested by some researchers, but most now think it is simply another version of Liopluridon ferox, rather than a completely separate species, mainly because there are not enough clear differences to prove otherwise. The fossils of Liopluridon are mostly found in Europe, especially in countries like England, France, and Germany, although there has also been a discovery in Mexico, showing that this predator may have had a wider range than once thought. Interestingly, the original specimen used to describe Liopluridon ferox is just a single tooth, and that tooth does not have many clear features that make it easy to identify. Because of this, modern scientists have suggested choosing a new reference specimen, called a neotype, to make sure the species can be properly defined and understood. Over time, other species names have been suggested, but most of these have later been rejected or reassigned to other related marine reptiles. Like other plesiosaurs, Liopluridon had a body perfectly adapted for life in the ocean. It had 4 strong flippers that it used to swim, a short tail, and a large head filled with sharp teeth. Unlike long-necked plesiosaurs, it had a short neck and a massive skull, which made it especially suited for hunting. In one famous television documentary released in the late 20th century, it was shown as an enormous creature reaching lengths of about 25 meters, but this was a major exaggeration. In reality, most fossil evidence suggests that Liopluridon was usually between about 4 and 8 meters long, though some scientists believe the very largest individuals may have reached around 10 meters. Even at this more realistic size, it would still have been a dominant predator in its environment. Liopluridon was likely an ambush hunter, meaning it would quietly approach its prey and then attack suddenly with great speed and force. Its diet probably included fish, squid-like animals known as cephalopods, and even other marine reptiles. With its strong jaws and sharp teeth, it would have been capable of delivering powerful bites, making it one of the top predators of the Jurassic seas. The story of how Liopluridon was discovered and named is long and somewhat confusing, filled with misidentifications and changing ideas. Even before the name Liopluridon was officially created, scientists had already found fossils that likely belonged to this animal. In the early 19th century, a scientist named Hermann von Meyer described a large tooth found in Switzerland and gave it the name Ichthyosaurus mariani. However, the tooth did not have enough unique features to clearly identify it, so its true identity remained uncertain. Later researchers suggested it might belong to Liopluridon, but there was never enough evidence to be sure, and it is now considered a doubtful name. Over the years, many other fossils were discovered and given different names, often because scientists did not yet fully understand how these marine reptiles were related to each other. Some teeth and bones were placed in groups like plesiosaurs, or even other genera, and sometimes the same name was accidentally used more than once, making it invalid. This created a tangled history where the same animal could be known by several different names, and different animals could be mistakenly grouped together. The name Liopluridon itself was finally created in the year 1873 by a scientist named Henri-Émile Sauvage. He based the name on 3 separate teeth, each thought to belong to different species at the time. The most important of these, the tooth that defines Liopluridon ferox, was found in France and is still kept in a museum today. The name reflects the smooth sides of the teeth, which made them stand out from those of other similar reptiles, while the species name ferox highlights the fierce nature suggested by its large and powerful teeth. After its naming, scientists continued to debate whether Liopluridon was truly a separate genus or just part of another group like Plesiosaurus. For many years, some researchers believed the differences were too small and grouped them together, while others argued that features such as the shape of the jaws showed clear distinctions. As more fossils were discovered, including skulls and nearly complete skeletons collected by fossil hunters like Alfred Leeds and his brother, scientists were able to study the animal in greater detail. These discoveries slowly helped to clarify what Liopluridon really looked like and how it lived. Throughout the 20th century, more studies were carried out, and opinions continued to change. Some scientists proposed new species within Liopluridon, while others argued that these differences were simply natural variation between individuals. By the early 21st century, many researchers concluded that most of the supposed species were not truly separate, leaving Liopluridon ferox as the only clearly valid species. Other names were either removed from the genus or reassigned to different groups of plesiosaurids. New discoveries have continued to add to our understanding. Fossils from Germany, France, and even Mexico have shown that Liopluridon lived across a wide area during the Jurassic period. In more recent years, scientists have also found more complete skeletons, including one discovered in France in the late 20th century, which is among the best preserved examples known. Even so, there are still questions left unanswered, especially because the original defining fossil is just a single tooth. This is why some researchers believe a new, more complete specimen should be officially chosen to represent the species, helping to bring clarity to its classification. Plesiosaurs can usually be grouped into 2 main body types. One type had a small head and a long, graceful neck, while the other had a large, powerful head and a short, thick neck. Liopluridon clearly belonged to this second group, built more like a living battering ram than a gentle swimmer. Like all plesiosaurs, it had a short tail, a wide and heavy body, and 4 large flippers shaped like paddles, which it used to move through the water. When the scientist Henri-Émile Sauvage first described Liopluridon in the year 1873, he believed that even a single tooth showed it must have come from an animal of truly gigantic size. Much later, in the year 1999, the creature became famous around the world after appearing in the BBC television series Walking with Dinosaurs. In that show, it was presented as a massive top predator, said to reach about 25 meters in length and weigh around 150 tons. This dramatic version was based on a single backbone bone found near Peterborough, which was used to estimate the animal's full size. At the time, this seemed believable, but later studies showed that this estimate was far too large. In fact, scientists later questioned whether that bone even belonged to Liopluridon at all. By the year 2019, it was finally identified as coming from a completely different animal, a long-necked plant-eating dinosaur. Scientists have tried to understand the real size of Liopluridon by comparing the length of its skull to the length of its body. Early ideas suggested that the skull made up about 1/7 of the total body length, but better fossil discoveries showed that the skull was actually closer to 1/5 of the entire body. Using this improved understanding, one large skull suggests a body length of about 6 meters. Smaller individuals may have been between about 5 and a little under 6 meters long, weighing roughly 1 to almost 2 tons. More recent research, published in the year 2024, estimates that the largest known specimen reached about 8 meters in length and weighed close to 8 tons. Some scientists still think a few individuals might have grown even larger, possibly exceeding 10 meters, but such sizes remain uncertain and are likely rare. Liopluridon belonged to a group of powerful marine reptiles called Thalassophonidae, which were part of the larger plesiosaur family known as Plesiosauridae. These animals lived from the middle part of the Jurassic period into the early part of the late Cretaceous and were found in oceans all over the world. Compared to their later relatives, earlier forms like Liopluridon tended to have slightly smaller bodies and skulls, along with differences in the number of teeth sockets in their jaws. Its body was perfectly designed for life as a hunter. With 4 strong, paddle-like flippers, Liopluridon could move through the water with great power. Although this style of swimming was not the most energy efficient, studies using robotic models have shown that it allowed for sudden bursts of speed. This would have been extremely useful for an ambush predator, letting it rush forward quickly to catch prey off guard. Its skull also reveals another interesting ability. It may have used its nostrils to detect smells in the water, helping it track down prey even when it could not see it clearly. A rare fossil, thought to belong to a young individual, gives a glimpse into what Liopluridon might have eaten. Inside its stomach were remains of squid-like creatures, fish bones, and even a single tooth from another reptile. However, the exact diet is still uncertain. One idea is that it mainly hunted squid, which were very common at the time, but since squid are fast swimmers, this would only work if Liopluridon relied on surprise attacks. Another possibility is that it was an opportunistic feeder, eating whatever it could find, from soft-bodied animals to other marine reptiles. There is also a more unusual idea that it preyed on animals that had already eaten squid, and the remains found were actually from the stomach contents of its prey. None of these explanations can be proven with complete certainty. The fossil also contained at least 7 smooth stones, known as gastroliths. These stones do not appear to have been used for grinding food, as they are often in other animals. Instead, they may have been swallowed by accident and simply remained in the stomach, or they could be the leftover remains of material that resisted the strong acids inside its body. Chronosaurus was a huge and powerful marine reptile that no longer exists today. It belonged to a group of animals known as plesiosaurs, which were famous for their massive heads, short necks, and strong bodies built for hunting. This creature lived during a time known as the early Cretaceous, in a warm ancient world that existed many millions of years ago in what is now Australia. The earliest fossil of this animal was discovered in the year 1899. It was only a part of the lower jaw, and at first it was mistakenly believed to belong to a completely different kind of sea reptile called an ichthyosaur. It was not until the year 1924 that the scientist Albert Heber Longman carefully studied the fossil and correctly identified it as belonging to a large and fearsome plesiosaur. He gave it the name Chronosaurus queenslandicus. The name Chronosaurus means lizard of Kronos, inspired by Kronos, a powerful figure from Greek mythology, reflecting the creature's great size and terrifying nature. The second part of the name honors Queensland, the region in Australia where it was first found, and this remains the only accepted species of this genus today. In the early part of the 1930s, a scientific expedition organized by Harvard University traveled to Australia and uncovered more fossils of this giant reptile. Among these discoveries was a famous skeleton that would later be reconstructed for display, although much of it had to be filled in with plaster, which led to some inaccuracies. Over time, more fossils were found, including 2 fairly large and partly complete skeletons. Because the original fossil used to name Chronosaurus was too incomplete to clearly define its unique features, scientists have suggested that these more complete skeletons could serve as better reference specimens in the future. At one point, 2 additional species were proposed, but later research showed that they were either doubtful or actually belonged to different kinds of animals. Chronosaurus is considered one of the largest plesiosaurs ever discovered. Early scientists believed it could grow to an enormous length of about 13 meters, based on the Harvard skeleton. However, this estimate turned out to be too large because the reconstruction included too many backbone bones. More careful studies carried out in the early 2000s suggested a smaller but still impressive size, ranging from about 9 meters to just over 10 meters in length. Like all plesiosaurs, Chronosaurus had 4 large paddle-shaped flippers, a short tail, and a broad, heavy body. Unlike long-necked plesiosaurs, it had a massive head and a short neck, making it perfectly suited for powerful attacks. The skull of Chronosaurus was truly enormous, even larger than the skulls of some of the biggest meat-eating dinosaurs that walked on land. The front of its head stretched forward into a long snout, and its lower jaw had a long fused section at the front where both sides met. This area held up to 6 pairs of large teeth. Its teeth were thick, cone-shaped, and built for gripping and crushing large prey. The teeth at the front of the mouth were especially large, helping it seize struggling animals. Its flippers were also impressive, with the back pair being even bigger than the front pair. When fully extended, these flippers could span more than 5 meters across, allowing it to move through the water with strong, sweeping motions. Modern studies place Chronosaurus within a group of plesiosaurs known as Brachioconinae, a family of large marine predators that lived throughout the Cretaceous period. Fossil evidence shows that it lived in a vast inland sea called the Eromanga Sea, which once covered a large part of Australia. This sea was not always warm. At times, its waters could become very cold, even close to freezing. Despite these harsh conditions, Chronosaurus thrived and likely ruled this environment as a top predator. Fossils reveal that it hunted large animals such as sea turtles and other marine reptiles, including its distant relatives. The power of its bite was extraordinary. Scientists estimate that its jaws could produce a force ranging from about 15,000 to 27,000 newtons, making it capable of crushing bone and tearing apart large prey. Evidence from fossils also suggests a darker side to its behavior. A young Chronosaurus skull has been found with bite marks that match those of an adult, hinting that these animals may have attacked each other, possibly even engaging in cannibalism. At the same time, it was not completely without rivals. Other large predators lived in the same sea, including fast-swimming sharks similar to Cretoxorina, and some Chronosaurus fossils show bite marks that may have come from such competitors. Because the original fossil of Chronosaurus is incomplete, much of what scientists know about its body comes from later discoveries that are more complete. These fossils show that, like all plesiosaurs, it had a short tail, a large and heavy body, and 2 pairs of powerful flippers that acted like underwater wings. Its body design made it an efficient and deadly swimmer, perfectly adapted to life in the ocean. Over the years, scientists have debated its true size. Early researchers believed it might have been even larger than another giant pliosaur from North America called Megalosaurus. Later, after more fossils were collected, many experts settled on a length of about 12.8 meters for one famous specimen. For a time, Chronosaurus was even thought to be the largest marine reptile ever discovered. However, in the year 1995, another giant marine reptile called Mosasaurus hoffmanii was suggested to be even larger, although newer studies later reduced its estimated size. Today, the title of the largest known marine reptile is often given to a gigantic ichthyosaur called Ecthyotatan, which may have reached an incredible length of about 25 meters. When scientists corrected the errors in the Harvard skeleton, they concluded that Chronosaurus was likely between 9 and 10.5 meters long and weighed around 11 tons. These measurements are now considered close to the maximum size for the animal. Other researchers have reached similar conclusions, with estimates generally falling between 9 and just over 10 meters. More recent studies have refined these numbers even further, suggesting a length of just over 10 meters for some of the largest individuals. Different fossils of Chronosaurus show that not all individuals were the same size. The original specimen, although very incomplete, may have been about 5.9 meters long and weighed nearly 2 tons. Another well-preserved specimen is thought to have reached about 8.9 meters in length and weighed around 6 to 7 tons. A particularly complete skeleton measures slightly smaller, at about 8.6 meters long and around 5 to 6 tons in weight. Some of the largest fossils ever found, discovered in a region known as the Toolbuck Formation, suggest individuals that reached lengths between just over 10 meters and 10.5 meters, with body masses that could have ranged from roughly 10 to over 15 tons. The lower jaws of Chronosaurus were built in a very striking and powerful way. At the front of the jaws, the two halves joined together in a long, stretched-out section that widened into a shape like a spoon. This part of the jaw was not only long, but also packed with teeth, holding as many as 6 pairs near the front. Each side of the lower jaw, known as the dentary, could carry up to 26 teeth, forming a deadly row of sharp weapons. The joint where the lower jaw connected to the skull had a curved, kidney-like shape and was tilted upward and inward, allowing the animal to snap its jaws shut with great force. The teeth themselves were one of the most unique features of this predator. They were shaped like cones, slightly ridged along their length, and lacked the sharp cutting edges seen in some other predators. Not all the teeth looked the same either. The ones at the front were larger and shaped like fangs, perfect for grabbing and holding onto prey, while the teeth farther back were smaller, thicker, and curved backward more strongly, helping to grip struggling animals and stop them from escaping. One of the most famous skeletons once believed to belong to this animal, kept at Harvard, was studied in detail in the year 1959 by the scientists Alfred Sherwood Romer and Lewis. However, much of this skeleton had been heavily rebuilt using plaster, making it difficult today to tell which parts are original fossil and which parts are artificial additions. Because of this uncertainty, the specimen is now sometimes placed under a different name, and future scans using advanced imaging might finally reveal whether it truly belongs to Chronosaurus or not. Even so, many other fossils of this creature include parts of the body beyond the skull. The most complete known specimen, identified as QMF10113, preserves a large portion of the body and is expected to provide important clues about the animal's full structure once it is studied in greater detail. From the fossils that have been studied, scientists believe that Chronosaurus had at least 35 vertebrae in front of the hip region, including 13 in the neck and 5 in the chest area. Unlike some of its relatives, the bones in its neck were broader than those in its back. The front part of the back had vertebrae that were taller than they were wide, and certain connecting joints that are usually seen in other animals were missing in parts of the spine. The ribs in the chest region were thick and strong, matching the equally sturdy bones they were attached to, and each rib had only a single head where it connected to the spine. Although no complete tail has been found, scientists believe that the end of the tail supported a small fin, similar to other plesiosaurs, helping with movement in the water. The bones of the chest and hips were long from front to back, giving the body a strong, streamlined shape. The rear flippers were longer than the front ones, and the thigh bone was both longer and stronger than the upper arm bone. This suggests that the back flippers were especially powerful, possibly spreading out wide enough to form a span of more than 5 meters, giving the animal strong propulsion as it swam. When this animal was first discovered, the scientist Charles Walter Davis thought the fossil might belong to an ichthyosaur, another type of marine reptile. But in the year 1924, Haber Albert Longman carefully studied the remains and placed it in the family Plesiosauridae, where it has generally remained ever since. Over the years, some scientists suggested different ideas about its classification. For example, in the year 1962, Samuel Paul Wells proposed that it might belong to another group, but that group is no longer considered valid today. The exact place of Chronosaurus within its family has been debated for many years. In the year 1992, Hampe suggested grouping it closely with Brachiochenius in a special family. This idea was supported a few years later by Kenneth Carpenter, although he pointed out some important differences in their skulls. Later, in the year 2001, F. Robin O'Keefe re-examined the group and suggested that Chronosaurus was more primitive and not as closely related to Brachiochenius as previously thought. Further studies continued to shift its position slightly, with some researchers placing it among more advanced members of its family, while others kept it closer to its earlier relatives. By the year 2013, a new grouping called Thalassophornia was created by Roger Benson and Patrick Druckenmiller. This group included the classic short-necked, large-headed plesiosaurs, and Chronosaurus was placed among them. Within a smaller group inside this category, it is often considered one of the most advanced members, closely related to both Brachiochenius and Megacephalosaurus. Later studies have continued to support this general placement. Most members of this group lived during the Cretaceous period and are often grouped together because of similarities in their teeth, which tend to be more rounded in cross-section compared to some earlier relatives. Many of them also show features that suggest a shift toward hunting smaller prey, such as longer snouts and more delicate jaws. However, Chronosaurus stands out as an exception. Its teeth vary greatly in shape, showing that it was not adapted for small prey like many of its relatives. Instead, its powerful jaws and varied teeth suggest it specialized in hunting large animals. With its huge size, powerful body, and wide distribution, Chronosaurus was most likely the top predator of the ancient inland sea that once covered parts of what is now Australia. Fossils even preserve the remains of its last meals. One famous specimen contains the remains of a sea turtle inside its body. The position of the turtle suggests that the animal may have choked and died while trying to swallow its prey. The turtle's size and shape are similar to those of Notocoloni, a common species from that time. There is also evidence that Chronosaurus attacked long-necked marine reptiles like Eromangosaurus. A crushed skull of this animal shows bite marks that match the teeth of Chronosaurus, suggesting it targeted the neck, a weak and vulnerable part of the body. Evidence also shows that Chronosaurus may have fought or even eaten its own kind. A smaller skull has been found with bite marks that match those of a larger individual. Scientists believe this smaller animal was likely a young individual, measuring less than 7 meters in length, while fully grown adults could reach about 10.5 meters. The injuries suggest that it may have been killed by an adult, possibly during an attack or act of cannibalism, though it is also possible the bites happened after death. One of the most impressive features of Chronosaurus was its incredible bite force. Studies using advanced methods have shown that its jaws were among the most powerful ever known. Estimates suggest it could bite with a force ranging from about 15,000 to over 27,000 newtons. This is stronger than the bite of any living animal today, and even rivals some of the most famous extinct predators like Tyrannosaurus. However, it still falls short of the enormous bite force of the giant shark Otodus Megalodon, which may have produced forces far greater. Even so, the bite of Chronosaurus was more than enough to crush bones, tear through flesh, and dominate the seas it ruled. Tylosaurus was a remarkable kind of marine reptile known as a mosasaur, a group of powerful predatory lizards that ruled the oceans. These enormous creatures swam through the seas roughly from 92 million to 66 million years ago, during the late stages of the Cretaceous period, long before humans walked the earth. Fossils of Tylosaurus have been found across the North Atlantic region, including parts of North America, Europe, and Africa, revealing just how widely they once roamed. Long before European explorers set foot in the Americas, the fossils of Tylosaurus had already caught the attention of Native American peoples. These early discoveries likely inspired many myths and stories, with some of the oldest accounts dating back well before the 1500s. People of the Great Plains spoke of a time when enormous water-dwelling creatures battled fierce thunderbirds and were sometimes petrified by their lightning. The abundance of gigantic marine fossils, including those of Tylosaurus and flying reptiles like Pteranodon, may have given rise to these dramatic legends. In the year 1804, the famous Lewis and Clark expedition stumbled upon a now-lost fossil skeleton beside the Missouri River. At the time, it was identified as a massive fish stretching approximately 45 feet, or around 14 meters, in length. Modern researchers have speculated about the true identity of this fossil. In 2003, Richard Ellis suggested it might belong to Mosasaurus missouriensis, while a study in 2007 by Robert W. Meredith and his team proposed it could have been a Tylosaurian mosasaur, pointing to Tylosaurus fossils already known from the Missouri River. They also noted the small chance it might have been an elasmosaurid plesiosaur, a rarer type of long-necked marine reptile found in the area. Tylosaurus holds a special place in the history of paleontology in North America. It was the third new genus of mosasaur ever described from the continent, following Cladastes and Platecarpus, and the first to be identified in Kansas. The early study of Tylosaurus was marked by the dramatic rivalry known as the Bone Wars between two legendary paleontologists, Edward Drinker Cope and Othniel Charles Marsh. In 1869, Cope described the type specimen, a partial skull nearly 5 feet or 1.5 meters long, along with 13 vertebrae, lent to him by Louis Agassiz, of the Harvard Museum of Comparative Zoology. The fossil came from the Niobrara Formation near Monument Rocks and close to Fort Hays, Kansas. Cope initially named it Macrosaurus proriger, borrowing the name from a European mosasaur genus. The species name, proriger, means prow-bearing, a nod to its long, pointed snout. The following year, Cope published a more detailed description, but, without explanation, moved it to another European genus called Liopluridon. 2 years later, in 1872, Marsh argued that Liopluridon proriger was unique and deserved its own genus. He first proposed the name Rhinosaurus, meaning nose lizard, from the Greek words for nose and lizard. Cope disputed this, suggesting Ramphosaurus instead, but that name was already taken. Finally, Marsh introduced the name Tylosaurus, again referencing the creature's knob-like snout. The formal transfer of the species to Tylosaurus was completed in 1873 by Joseph Leidy, and this name gradually became widely accepted, though Cope continued to use Liopluridon for some time. Throughout the late 19th and 20th centuries, more fossils were found and added to the genus. Cope described another species in 1874, initially calling it Liopluridon nepaiolicus, based on remains found by geologist Benjamin Franklin Mudge near the Solomon River. Later, in 1894, John Campbell Merriam officially placed it in the genus Tylosaurus. By 1967, Dale A. Russell recognized only 2 valid species, Tylosaurus proriger and Tylosaurus nepaiolicus, though additional species discovered around the world over the years were eventually reassigned to Tylosaurus. In 1885, a nearly complete but poorly preserved skeleton found in a phosphate quarry in Belgium was named Hinosaurus bernardi by Louis Dallo, meaning lizard from the Haine River. Later, in 1988, Elizabeth Nichols described a second species from Manitoba, Canada, naming it Hinosaurus pembinensis after the Pembina member of the Pierre Shale. By 2010, researchers Timon Bullard and Michael Caldwell reclassified both species under Tylosaurus as Tylosaurus pembinensis and Tylosaurus bernardi, though some still debate whether Hinosaurus should remain a separate genus due to differences in teeth. Other species of Tylosaurus continued to be identified in Europe, North America, and Africa. In 1896, a partial skull from France was described as Mosasaurus gaudrii, later reassigned to Tylosaurus in 2005. In Sweden, fossils discovered near Ivo Lake in the Kristianstad Basin led to a species first described in 1963 as Mosasaurus hoffmanni ivoensis and later reassigned to Tylosaurus, though debate about its proper placement continues. In Angola, a partial skull from the Itombe Formation was named Mosasaurus iambensis in 1964 and reassigned to Tylosaurus in 1992, though the original fossil was destroyed in a fire. More recently, in the 21st century, several new species have been described. In 2005, Tylosaurus kansasensis was described from fossils in Kansas, though later studies suggested it might be a juvenile form of Tylosaurus nepaiolicus. In 2006, Bullard introduced Tylosaurus saskatchewanensis, nicknamed Omik-UW, meaning hunter in Cree, based on a partial skeleton from Saskatchewan. In 2020, a partial skull from Alberta was named Tylosaurus borealis, representing the northernmost known occurrence of the genus. Tylosaurus was a remarkable type of mosasaur, a late-evolving marine lizard that had developed advanced adaptations for life entirely in the ocean. Unlike its earlier relatives that might have resembled giant sea snakes, Tylosaurus had a body perfectly shaped for swift movement through water. Its body was long and streamlined, ending in an extended tail with a downward bend that supported a 2-lobed tail fin, while 2 pairs of strong, paddle-like flippers allowed it to maneuver with precision. Over time, scientists realized that Tylosaurus and its relatives were more comparable in body plan to other large marine animals, such as ichthyosaurs, marine crocodiles, and ancient whales, even though they were not directly related, a striking example of convergent evolution, where very different animals evolve similar forms to adapt to similar environments. Some species of Tylosaurus rank among the largest mosasaurs ever discovered. The most complete and famous specimen, a skeleton of Tylosaurus proriger, held at the University of Kansas Natural History Museum and nicknamed Bunker, has been estimated to measure between 12 and 15 meters in length, which is roughly 39 to 52 feet. Another, more fragmentary skeleton from the Sternberg Museum of Natural History may have belonged to an even larger individual. Paleontologist Michael Everhart estimated this specimen could have come from a Tylosaurus, around 14 meters long, compared to his 12-meter estimate for Bunker. Over time, Tylosaurus species followed what is known as Cope's rule, in which the body size of a lineage tends to increase as millions of years pass. In North America, the earliest Tylosaurus lived during the Turonian and Coniacian stages, roughly 90 to 86 million years ago. These early species, such as Tylosaurus nepialicus and its ancestors, were more modest in size, usually ranging from 5 to 7 meters long, about 16 to 23 feet, and weighing between 200 and 500 kilograms, or roughly 440 to 1,100 pounds. By the Santonian stage, around 86 to 83 million years ago, T. nepialicus and the newly emerging T. proriger had grown larger, reaching 8 to 9 meters in length, around 26 to 30 feet, and weighing approximately 1,100 kilograms, or about 2,400 pounds. During the early Campanian, T. proriger reached impressive lengths of 13 to 14 meters, roughly 43 to 46 feet. Everhart suggested that because mosasaurs grew continuously throughout their lives, exceptionally old individuals could theoretically have reached 20 meters, or about 66 feet, though no fossils exist to confirm this extreme size. Other species from the Campanian to Maastrichtian periods were similarly massive. The largest estimate for Tylosaurus bernardi, according to Lindgren in 2005, is 12.2 meters, roughly 40 feet, although earlier studies mistakenly suggested sizes between 15 and 17 meters, or 49 to 56 feet. The Royal Saskatchewan Museum reconstructed T. saskatchewanensis at over 9.75 meters, around 32 feet. A mounted skeleton of T. pembinensis, affectionately called Bruce, at the Canadian Fossil Discovery Centre, measures 13.05 meters, about 42 feet 8 inches, earning a Guinness World Record in 2014 for being the largest mosasaur on display, though later studies indicated the skeleton was slightly exaggerated in vertebrae count. Tylosaurus borealis is estimated at 6.5 to 8 meters, around 21 to 26 feet long. The skull of Tylosaurus was another marvel. The largest known skull, belonging to the Bunker specimen, measures approximately 1.7 meters, or 5 feet 6 inches, and typically accounts for 13 to 14% of the total body length. Its head was conical, and its snout was proportionally longer than in most mosasaurs, with the exception of Ectenosaurus. The most distinctive feature of Tylosaurus is its elongated snout, or rostrum, which gave the genus its name. This rostrum began small and sharply pointed at birth, but quickly grew into a thick, blunt knob. It was strongly built, reinforced by a broad internarial bar formed from fused skull bones, and contained passageways for trigeminal nerves through numerous small openings on the snout and along the upper jaw above the gum line. The nostrils of Tylosaurus were unique, bordered differently than in other mosasaurs, and their position varied slightly between species. In T. proriger and T. pembinensis, the nostrils opened above the fourth upper jaw tooth, in T. nepialicus between the third and fourth, and in T. bernardi just behind the fourth. Nostrils were proportionally short in T. proriger, T. bernardi, and T. gaudrii, and longer in T. pembinensis. The nasal bones were loosely attached to the rest of the skull, which may explain why they are rarely preserved in fossils, making Tylosaurus one of the few mosasaurs with well-documented nasal bones. The internal passageways from the nostrils to the throat, called choanae, were shaped like compressed teardrops and bordered by other skull bones. Ahead of these choanae, each vomer bone bordered the fenestra for the Jacobson's organ, used for detecting smells with the tongue. The skull featured a low midline crest on the frontal bone, more prominent in T. proriger and moderately present in T. saskatchewanensis and T. bernardi. The eyes were surrounded by overlapping bones in a distinctive pattern, with the jugal bone forming an L-shaped bottom edge with a small, hook-like extension. At the rear of the skull, the quadrate bones connected the lower jaw to the cranium and supported the eardrums. Their complex shapes varied with age and species, starting hook-like in juveniles and becoming robust and oval in adults. These bones also carried processes for jaw muscles, showing changes as individuals matured. The lower jaw was composed of several bones fused or articulated together, with Tylosaurus having a total of 13 dentary teeth and up to 13 upper jaw teeth. The teeth were mostly uniform in size and shape, triangular, slightly recurved, and serrated along the cutting edges, ideal for slicing through large marine prey. Some teeth were adapted for piercing or smashing, depending on the species. The pterygoid teeth in the roof of the mouth may have helped hold prey in place, while the lower jaw slid back and forth, functioning like a ratchet. The lower jaw, or dentary, was long and robust, forming over half of the jaw's total length. The ventral edge was mostly straight or slightly curved, with a small ridge appearing in adult T. proroger. Overall, Tylosaurus had a powerful and specialized bite, with teeth and jaws finely tuned for hunting large marine animals, making it one of the ocean's most formidable predators of its time. Adult Tylosaurus had both its pectoral and pelvic girdles unfused, which sets it apart from some other mosasaurs, such as Prognathodon overtoni. Its shoulder blade, or scapula, was much smaller than the coracoid bone, and it lacked certain features seen in other mosasaurs, such as a notch at the front of the coracoid and a prominent pubic tubercle. The limbs of Tylosaurus were relatively primitive compared to other mosasaurs. The humerus in the forelimb and the femur in the hind limb, collectively called stylopodia, did not have the highly complex muscle attachment areas or the extreme shortening seen in more advanced species. The wrist and ankle bones, called carpals and tarsals, were mostly unossified, meaning they were not fully hardened into bone. Whereas most other mosasaurs had between 3 and 5 ossified carpals and tarsals, adult Tylosaurus never had more than 2 fully ossified bones in each, usually just the ulnar in the wrist and the astragalus in the ankle. Its fingers and toes had extra bones, a condition called hyperphalangy, and these phalanges were spindle-shaped, unlike the short, blocky, hourglass-like shapes found in mosasaurians. In addition, the pisiform bone in the wrist appeared to be absent or never ossified. How these differences in limb structure affected swimming and movement across mosasaur species is still uncertain. Tylosaurus had a long and flexible spine, with about 29 to 30 presacral vertebrae, those in front of the hips, 6 to 7 pygal vertebrae, those just behind the hips, and between 89 and 112 tail vertebrae. Because there was no solid bony connection between the hip bones and the spine, it is unclear whether any mosasaurs had true sacral vertebrae. Like some related groups, Tylosaurus had chevrons, bones under the tail vertebrae, that were attached but not fused, and its tail curved distinctly downward, hinting at the presence of a tail fluke, like a rudder, for powerful swimming. Fossils of Tylosaurus have revealed details about its skin, first reported in the late 1870s. Its skin was covered in small, diamond-shaped scales arranged in diagonal rows, similar to those of modern rattlesnakes and other reptiles, though the scales were tiny compared to the size of the animal. In a 5-meter-long individual, each scale measured roughly 3.3 by 2.5 millimeters, and a single square inch of its belly contained about 90 scales. These scales were keeled, like shark teeth, which likely helped reduce water resistance and the reflection of light underwater. Microscopic studies of a Tylosaurus nepiolicus specimen by Lindgren and colleagues in 2014 found high levels of eumelanin, a pigment that produces dark coloring. This suggests the mosasaur may have had a dark, leatherback, sea turtle-like hue, possibly with countershading, where the underside is lighter than the back, as seen in many aquatic animals. Dark coloration would have offered several advantages, such as absorbing heat to maintain body temperature in cooler waters, promoting rapid growth in juveniles, providing camouflage, protecting the skin from sunlight, and potentially even increasing aggression through certain genetic effects. Tylosaurus belongs to the family Mosasauridae, within the larger group Mosasauroidea, and is the defining genus of its own subfamily, the Tylosaurini. Other members of this group include Tannuosaurus and possibly Kaikaifilu. The subfamily is defined by a long, toothless front portion of the snout, called the premaxillary rostrum. Its closest relatives include the Pleioplatycarpini and the more primitive Tethysaurini and Jaguarosaurini. Together, these groups form one of 3 major evolutionary lineages of mosasaurs, first recognized in 1993 and later named Russellosaurina by Polkin and Bell in 2005. Tylosaurus was one of the earliest advanced mosasaurs. The oldest known fossil of the genus is a premaxilla, catalogued as TMM 40092-27, found in Middle Turonian age deposits of the Arcadia Park Shale in Texas, dated between 92.1 and 91.4 million years ago using fossil correlations. Initially, it was referred to as Tylosaurinae incertae sedis, but was later reassigned to T. kansasensis during a re-examination in 2020. A slightly younger specimen, a skull labeled SGM-M1 from the Ojinaga Formation in Chihuahua, Mexico, dates to roughly 90 million years ago and represents a Tylosaurus similar to T. kansasensis. A tooth found in late Maastrichtian deposits in Nasiław, Poland, close to the Cretaceous-Paleogene boundary, has been assigned to Hinosaurus sp., which is now considered synonymous with Tylosaurus, making this genus one of the last surviving mosasaurs. Currently, 8 species are recognized as valid: T. proriger, T. nepaolicus, T. bernardi, T. gaudrii, T. avoensis, T. iambensis, T. pembenensis, and T. saskatchewanensis, while the status of T. kansasensis and T. borealis remains debated. As one of the largest marine predators of its time, Tylosaurus occupied the top of its ecosystem's food chain, preying on a vast array of creatures. Fossils have revealed that its diet included other mosasaurs, plesiosaurs, turtles, birds, bony fish, and sharks. Bite marks indicate it also hunted giant squid and ammonites. The impressive appetite of Tylosaurus is illustrated by a 2019 find from the Pierre Shale of South Dakota, where a single T. proriger skeleton measuring 8.8 meters long contained the remains of a mosasaur over 2 meters long, a diving bird called Hesperornis, a fish named Bananogmius, and possibly a shark in its stomach. Other finds include a sea turtle in a T. bernardi-like species, a Dolichor hinchops measuring 2.5 meters inside another T. proriger, and partially digested remains of Similichthys, Cladastes, Platecarpus, and Plioplatycarpus in various Tylosaurus species. Fossil bite marks on ammonites, Protostega shells, and the gladius of Encoteuthis have also been attributed to this predator. There is even evidence suggesting Tylosaurus occasionally scavenged dinosaur carcasses. In 2001, Pash and May reported bite marks on a hadrosaur skeleton from the Turonian age Matanuska Formation in Alaska, interpreted as scavenging from a floating carcass rather than predation. However, this has been debated, since T. proriger did not appear until the Santonian and was mostly restricted to the western interior seaway, though relatives existed in Turonian deposits in Russia's Chukotsky district. Interactions among Tylosaurus may have been aggressive. Fossils show injuries inflicted by other Tylosaurus, often near the head, suggesting non-lethal encounters. Some modern lizards bite their mates during courtship or rivals during territorial disputes, and Tylosaurus may have behaved similarly. One particularly dramatic example comes from the holotype of T. kansasensis, which shows evidence of a fatal encounter with a larger Tylosaurus around 7 meters long. The skull bore 4 deep gouges, the lower jaw had at least 7 punctures, and the neck vertebrae were twisted unnaturally. Analysis suggests the larger mosasaur attacked from below, rolled its victim, crushed the skull, twisted the jaw, and severed the spinal cord, resulting in a swift death. Dunkleosteus was a giant, extinct fish that lived a very long time ago, during the late Devonian period, roughly 382 to 358 million years ago. Unlike many of its contemporaries, it swam in open oceans rather than sticking close to the sea floor, making it a pelagic predator. Dunkleosteus was one of the first vertebrates to reach the top of the food chain, ruling its underwater world with speed and power. Fossils of this ancient fish have been discovered across the globe, including in what are now the United States, Canada, Poland, Belgium, and Morocco. This fascinating genus includes 10 named species, although scientists are still debating whether all of these truly represent separate species. Among them are D. terrelli, D. belgicus, D. denisoni, D. marcesi, D. magnificus, D. missouriensis, D. newberry, D. ambliodoratus, D. raveri, and D. tudorensis. Of these, the most famous and best understood is D. terrelli, which also serves as the type species for the genus. Some of these species rank among the largest plate-skinned placoderms ever to roam the seas, their bodies armored in thick bony plates that serve both as protection and as a structural framework. Because almost none of Dunkleosteus's bodies have survived intact, scientists have had to estimate their size in many different ways. Early estimates of D. terrelli suggested lengths anywhere from 4.1 to 10 meters long, roughly 13 to 33 feet, and weights between 1 and 4 metric tons, or 1.1 to 4.4 short tons. However, more careful studies today suggest that it was likely smaller than previously thought, with ordinary adults measuring about 3.4 meters or 11 feet in length, and exceptionally large individuals reaching up to 4.1 meters or 13 feet. Its body weight for a typical adult is now estimated at roughly 950 to 1,200 kilograms, or about 2,090 to 2,650 pounds, while the largest individuals may have weighed between 1,494 and 1,764 kilograms, or roughly 3,394 to 3,889 pounds. One of the most remarkable features of Dunkleosteus was its jaw. Its mouth could open and close with incredible speed, possibly creating suction to help pull in prey, similar to modern-day suction-feeding fish. Its bite was extremely powerful, perhaps among the strongest of any fish that ever lived, though some recent studies have questioned just how extreme it really was. The story of Dunkleosteus's discovery is almost as fascinating as the fish itself. In 1867, a hotel owner and amateur fossil collector named J. Terrell discovered the first specimens along the cliffs near Lake Erie in Sheffield Lake, Ohio, just west of Cleveland. Terrell generously donated his collection to the Ohio Geological Survey and to John Strong Newberry, a prominent geologist. In 1873, Newberry officially described the fossils as a new genus and species, naming it Dinichthys hertzeri. But as more fossils were unearthed, it became clear by 1875 that multiple large fish species had existed in the Ohio Shale. The most common species, coming from the younger Cleveland Shale rather than the lowermost Huron Shale, was named Dinichthys terrelli in honor of Terrell. Sadly, most of Terrell's original collection was lost in a fire in Elyria, Ohio, in 1873. Today, the Cleveland Museum of Natural History holds the largest collection of Dunkleosteus fossils in the world, including the spectacular specimen CMNH 5768, the largest well-preserved individual of D. terrelli. Smaller but important collections exist at the American Museum of Natural History, the Smithsonian National Museum of Natural History, the Yale Peabody Museum, the Natural History Museum in London, and the Cincinnati Museum Center. Many museums display casts of CMNH 5768, allowing visitors worldwide to see the impressive armor and skull of this ancient predator. The fish's head and front body were encased in heavy bony plates, sometimes described as 2 to 3 inches thick or roughly 5 to 8 centimeters, though this extreme thickness applies mainly to the neutral plate at the back of the skull. The rest of the body had thinner armor, around 1/3 to 1 inch thick, or approximately 0.8 to 2.5 centimeters. These plates had a dual-layer structure with a hard outer layer and a spongy marrow-like inner layer, more like the bones of land-dwelling vertebrates than modern fish. Because mostly only the armored head and front portions fossilized, the rest of the fish remains a mystery. Less than 5% of Dunkleosteus specimens preserve more than a quarter of the skeleton, which has forced paleontologists to reconstruct the tail and hindquarters based on smaller related armored fish like Cocosteus. This has led to wildly different size estimates over the years. The spine of Dunkleosteus was unusually stiff. Its stiffened trunk, coupled with specialized connective tissues, likely allowed the fish to transmit powerful forces from its front body to its tail, much like modern fast-swimming predators such as tunas and lamnid sharks. The pelvic fins were relatively small, probably located near the end of the armored ventral shield, similar to other placoderms, and a rare fossil even preserved the outline of a pectoral fin, showing that placoderm fins were more varied than previously thought. Reconstructing the exact size of Dunkleosteus has been a challenge. The most careful studies suggest that typical adult D. terrelli measured around 3.4 meters, or 11 feet, with very large individuals reaching 4.1 meters, or 13 feet. Earlier claims of lengths exceeding 5 meters, or 16 feet, are now seen as unlikely. Even within statistical margins of error, lengths above 4.5 meters, or 15 feet, would require body proportions that simply do not match the fossil evidence. Despite the uncertainties, Dunkleosteus remains one of the most awe-inspiring predators of the Devonian seas, a true armored giant that combined speed, power, and a fearsome bite to dominate its ancient world. Its fossils continue to fascinate scientists and the public alike, revealing a glimpse of life in a time hundreds of millions of years before humans would ever appear on Earth. Dunkleosteus torelli, the giant armored fish of the late Devonian seas, had an extraordinary jaw system unlike anything seen in most other fishes. Its jaws operated through a clever four-bar linkage mechanism, a sort of biological machine made up of the skull, the thoracic shield, the lower jaw, and the powerful jaw muscles, all connected with movable joints. Scientists using biomechanical models, like Anderson and Westneat, proposed that this system allowed Dunkleosteus to open its massive jaws incredibly fast. Its jaws could snap open in just 20 milliseconds, and the entire opening and closing process could be completed in about 50 to 60 milliseconds. This is roughly the same speed as some modern fish that use suction to pull prey into their mouths. But unlike most fish today, Dunkleosteus could also deliver jaw-closing forces of mind-boggling strength. Early estimates suggested it could bite with a force of 4,414 newtons at the jaw tip and 5,363 newtons at the blade-like edges of its jaws. Some later calculations even pushed these numbers higher, to 6,170 newtons at the tip and 7,495 newtons at the blade edge, making Dunkleosteus arguably the strongest biter known among both living and extinct fishes, and among the fiercest of all animals. These immense pressures would have been strong enough to pierce or slice through armor-like skin and shells, indicating that Dunkleosteus was perfectly equipped to hunt heavily protected prey, such as ammonites and other armored placoderms. However, in the year 2025, Engelmann and colleagues questioned the idea that Dunkleosteus used suction to catch prey. They argued that previous models did not fully match the fish's anatomy. Instead, they suggested that the sharp, blade-like teeth of Dunkleosteus resembled those of predators that actively chased and tore apart their prey, rather than suction-feeding fish that rely on creating a vacuum to pull food in. Most suction feeders, they explained, have limited jaw openings and small, dense tooth patches, which are not designed for slicing large prey. Dunkleosteus, with its enormous jaws, would have been inefficient at creating suction. Engelmann and his team also noted that living in open water would make suction feeding on large prey especially unreliable because water resistance would reduce the effect. They proposed that Dunkleosteus's skull contained more cartilage than previously believed, including in key jaw joints and muscle attachment areas, allowing it to open its mouth to at least 65 to 70 degrees. This could mean that previous estimates of its bite force may need to be revised to fit this new understanding of its anatomy. Fossil evidence supports the idea that Dunkleosteus was a fast and aggressive predator. Teeth from a fast-swimming fish called Oridus were discovered alongside Dunkleosteus remains, probably indicating that these were once eaten and regurgitated. Oridus was a pelagic, high-speed fish, suggesting that Dunkleosteus had the speed and skill to chase down quick prey, contradicting earlier ideas that it was slow-moving. Many Dunkleosteus fossils are found with clusters of partially digested fish bones, hinting that this giant fish may have often regurgitated the hard parts of its prey rather than digesting them fully. Adults seem to have preferred deeper waters, while younger individuals may have lived in shallower seas, following a pattern seen in other placoderms. Interestingly, some fossil specimens show puncture marks that may have been caused by the fangs of other Dunkleosteus, suggesting aggressive interactions even among members of the same species. Dunkleosteus and its placoderm relatives were possibly among the first vertebrates to evolve internal fertilization of eggs, a feature seen in some modern sharks. In fact, some placoderms appear to have been viviparous, giving live birth, with fossils even showing structures that might have functioned like umbilical cords. Remarkably, studies of juvenile Dunkleosteus jaws reveal that even young individuals had jaws as robust as adults, capable of generating powerful bite forces. This means that even at smaller sizes, juvenile Dunkleosteus could tear into tough prey, following a very different growth pattern from most land-dwelling vertebrates, where young animals typically have much weaker, more delicate jaws than adults. Mosasaurus is the defining example of the Mosasauridae, a family of extinct aquatic reptiles that were part of the same group as modern lizards and snakes. These giant sea creatures lived roughly from 82 million to 66 million years ago, during the later part of the Cretaceous period, specifically the Campanian and Maastrichtian stages. Mosasaurus was among the first Mesozoic marine reptiles ever discovered and studied by scientists. The earliest fossils, mostly skulls, were uncovered in a chalk quarry near the Dutch city of Maastricht in the late 18th century. At first, these bones were mistaken for crocodiles or whales. One particularly large skull, discovered around the year 1780, became famous and was nicknamed the Great Animal of Maastricht. In the year 1808, the pioneering French naturalist Georges Cuvier studied these fossils and concluded that they belonged to a giant marine lizard. He noted similarities to monitor lizards, yet the creature was unlike anything alive today. Cuvier's recognition of Mosasaurus as a completely new type of animal was revolutionary at the time and played an important role in developing the concept of extinction, which was not widely accepted back then. The scientific name Mosasaurus was not given by Cuvier himself. It was later assigned in the year 1822 by William Daniel Conybeare, who named the genus after the Meuse River, where the first fossils were found. Even today, scientists debate exactly where Mosasaurus fits among modern reptiles, arguing whether its closest living relatives are monitor lizards or snakes. The largest species, Mosasaurus hoffmanni, is estimated to have reached a length of up to 12 meters, which is about 39 feet. Its skull was massive, with extremely strong jaws and muscles capable of delivering terrifyingly powerful bites. Its mouth held dozens of large, sharp teeth perfect for cutting through prey. Mosasaurus had 4 limbs that had evolved into broad paddle-like shapes, ideal for steering through water. Its long tail ended in a downward bend with a fluke that acted like a fin, giving it incredible swimming speed and maneuverability. The animal had excellent eyesight to make up for a weak sense of smell, and its high metabolism suggests it was warm-blooded, a rare trait among lizards, found only in mosasaurs. Species of Mosasaurus varied widely in form. While M. hoffmanni was robust and heavily built, other species like Monsieur Lemonnieri were more slender and snake-like. For centuries, the type species M. hoffmanni was poorly described, leading to confusion, and over 50 species were once mistakenly grouped under Mosasaurus. A detailed re-examination of the type specimen in the year 2017 clarified its classification, confirming at least 5 species in the genus, while another 5 still await reassessment. Fossil evidence shows that Mosasaurus lived across much of the ancient Atlantic Ocean and its surrounding seas. Remains have been found in North and South America, Europe, Africa, Western Asia, and even Antarctica, demonstrating that it could survive in tropical, subtropical, temperate, and near-polar waters. Mosasaurus was a top predator in these seas, feeding on nearly any animal it could catch, including bony fish, sharks, squid-like cephalopods, seabirds, sea turtles, and even other marine reptiles, including smaller mosasaurs. It probably hunted near the surface in open water. Its presence profoundly shaped marine ecosystems. For example, when Mosasaurus appeared in the western interior seaway of North America, it coincided with dramatic changes in the local marine animal communities. Despite competition from other giant predators like Prognathodon and Tylosaurus, Mosasaurus coexisted with them by hunting different prey or using different strategies, though conflicts still occurred. Fossils show that Mosasaurus sometimes fought with members of its own species, likely grappling with their snouts, much like modern crocodiles, and even attacks by other mosasaurs have been documented. The story of Mosasaurus's discovery is fascinating and full of adventure. The very first fossil known to science was a skull found in the year 1764 in a chalk quarry near Maastricht in the Netherlands, initially thought to belong to a whale. This specimen, now catalogued as TM7424, is preserved today at the Taylor's Museum in Haarlem. Around 1780, a second skull appeared in the same quarry and drew the attention of Johann Leonard Hoffmann, who believed it was a crocodile. Hoffmann contacted the scholar Petrus Camper, who published a study in 1786 describing it as a whale. The fossil became internationally famous, and during the French Revolutionary Wars in 1794, French forces looted it from Maastricht. It was sent to the National Museum of Natural History in Paris in 1795 and catalogued as MNHN AC 9648. a story recounted by Barthélemy Faujas de Saint-Fond in 1799, claimed 12 grenadiers retrieved it in exchange for 600 bottles of wine, though historians now think this tale was exaggerated. By the year 1800, Camper's son, Adriaan Gilles Camper, concluded that the second skull, the great animal of Maastricht, was actually a marine reptile related to monitor lizards. Georges Cuvier confirmed this in a detailed study published in 1808, showing it was a completely extinct type of lizard. This fossil played a key role in Cuvier's early ideas about extinction and catastrophism, concepts that laid groundwork for modern evolutionary theory. In North America, the Lewis and Clark expedition found a now-lost skeleton along the Missouri River in the year 1804, which was described as a 49-foot-long or 15-meter-long fish. Some modern researchers think this might have been the first discovery of the species Mosasaurus missouriensis, although other interpretations exist. In 1818, a fossil from Monmouth County, New Jersey, became the first North American specimen correctly identified as a Mosasaurus. The type specimen of M. missouriensis was described in 1834 by Richard Harlan, based on a fragment of a snout found near the Big Bend of the Missouri River. He named it for the river, initially thinking it was a type of ichthyosaurus, and later as an amphibian called Batrachiosaurus. The rest of the skull, found earlier by a fur trapper, ended up in the collection of Prince Maximilian of Wied-Neuwied between 1832 and 1834. The skull, now catalogued as RFUIP 1327, was studied by Georg August Goldfuss and published in 1845. That same year, Christian Erich Hermann von Meyer suggested the skull and Harlan's snout belonged to the same individual. Although the snout was considered lost at the time, Joseph Leidy officially named it Mosasaurus missouriensis in 1857. Remarkably, the snout was rediscovered in the year 2004 in the museum collection, under the catalog number MNHN 9587, confirming the earlier suspicions. Another species, M. conodon, was first described in 1881 by Edward Drinker Cope from a partial skeleton found in New Jersey, now catalogued as AMNH 1380. Cope thought it was a giant Cladastes and named it Cladastes conodon. In 1966, Donald Baird and Gerard R. Case reclassified it as a Mosasaurus. The name conodon likely comes from the ancient Greek words for cone and tooth, referring to the smooth, conical teeth of the species. Mosasaurus was one of the most advanced types of mosasaurs, a group of giant marine lizards that had fully adapted to life in the oceans. Unlike its earlier relatives that may have still ventured onto land, Mosasaurus was built for life entirely in water. Its body was long, streamlined, and shaped for cutting through the waves with ease. The tail was especially striking, stretched out and ending in a downward curve that supported a two-lobed fin, giving it strong propulsion. It had two pairs of paddle-like flippers that allowed it to steer and maneuver with agility. Long ago, scientists often imagined these advanced mosasaurs as enormous, flippered sea snakes, but modern studies show that in shape and movement, they resembled other large marine predators like ichthyosaurs, marine crocodilomorphs, and early whales, a result of convergent evolution where very different animals evolve similar body plans to thrive in the same environment. The most famous species, Mosasaurus hoffmanni, is considered one of the largest marine reptiles ever discovered, though most of what we know about it comes from skulls rather than complete skeletons. In one classic study from 1967, the researcher Russell suggested that the jaw of M. hoffmanni was about 1/10 the total body length. Using this idea, Grigoriev in 2014 measured the largest lower jaw known from this species, the Penza specimen, which was 171 centimeters long, or about 67 inches, and estimated the creature could have reached a staggering length of 17 meters, or 56 feet. Other estimates, using slightly smaller jaws, suggested it could have grown up to 17.5 meters, or 58 feet. However, later studies questioned whether this 1-to-10 ratio was too generous. In 2014, Federico Fanti and colleagues argued that the total length was probably closer to 7 times the skull length, based on a nearly complete skeleton of a close relative, Prognathodon overtoni. Using this ratio, a mosasaurus with a skull longer than 145 centimeters, or 57 inches, would measure about 11 meters, or 36 feet, and weigh around 10 metric tons or 11 short tons. Using the same 7-to-1 ratio, Gayford and colleagues in 2024 estimated that the Penza specimen would have measured about 12 meters or 39 feet long. Fossils suggest that some M. hoffmanni individuals may have been even bigger than the Penza specimen. One remarkable bone, a quadrate, was 1.5 times larger than average. Everhart and colleagues in 2016 suggested that, if scaled up, this individual could have reached around 18 meters, or 59 feet, though they did not specify the method used for this estimate. Gayford and colleagues later noted that they likely followed Russell's older ratio. Other Mosasaurus species were generally smaller than M. hoffmanni, but their skeletons are more complete. Mosasaurus lemonieri, for example, is known from several Belgian skeletons, and early researcher Dallo estimated it reached about 7 to 10 meters, or 23 to 33 feet, long. He observed that the skull made up roughly 1/11 of the total body length. Mosasaurus missouriensis may have grown to 8 or 9 meters, or 26 to 30 feet, based on a study in 2014. Large M. missouriensis skulls could exceed 1 meter, or about 3 1/3 feet. A particularly complete specimen measured 6.5 meters, or 21 feet, with a skull nearly 1 meter long. Mosasaurus biogai, from Morocco, is estimated to have grown 8 to 10 meters, or 26 to 33 feet, with skulls around 1 meter. Mosasaurus conodon is considered small to medium-sized, with its skull measuring just under 1 meter, or 38.5 inches. The skull of Mosasaurus was conical and tapered to a short snout that extended slightly past the front teeth. In M. hoffmanni, this snout was blunt, while in M. lemonieri it was more pointed. Both jaws had rows of small pits called foramina, which held the tips of nerves running through the jaws, forming patterns similar to those seen in Cladastes skulls. The upper jaws were generally robust, wide, and deep, except in M. conodon, which had more slender jaws. The lower jaw, or dentary, was long and straight in all species, although in M. hoffmanni, the top edge curved slightly upward, as did the largest M. lemonieri specimens. Other M. lemonieri skulls had nearly straight jaws. The premaxillary bar, a narrow bone behind the front teeth, tapered in M. hoffmanni and M. lemonieri, while it was sturdier in M. missouriensis. The nostrils were moderately sized, making up about 21 to 24% of the skull length in M. hoffmanni, and were positioned further back than in most other mosasaurs, beginning above the 4th or 5th upper teeth. Inside the skull, the palate was tightly packed for stability, and the brain case was relatively small and narrow, especially when compared with smaller mosasaurs like Plioplatycarpus marschi, whose brain was about twice as large despite being half the body length. The spaces for the cerebral hemispheres and occipital lobes were narrow, indicating smaller brains. The parietal foramen, linked to the parietal eye, was the smallest among mosasaurs. The quadrate bone, forming the jaw joint, was tall and rectangular rather than round and housed hearing structures, including the eardrum in a concave depression called the tympanic ala. The trachea likely extended from the esophagus to beneath the back of the lower jaw, splitting into smaller bronchi. Mosasaurus teeth were highly specialized for hunting, with surfaces made of prismatic enamel and 2 sharp cutting edges. Most species had large, strong teeth, except for the more slender teeth of M. conodon and M. lemonieri. The cutting edges were finely serrated in M. hoffmanni and M. missouriensis, while they were smooth in M. conodon and M. lemonieri, and finely wrinkled or crenulated in M. baugai. The number of enamel prisms varied by species. M. hoffmanni had 2 to 3 on the side facing the lips. M. missouriensis had 4 to 6 on the lips and 8 on the tongue side. M. lemonieri had 8 to 10 on the lips, and M. baugai had 3 to 5 on the lips and 8 to 9 on the tongue side. Mosasaurus had 4 types of teeth, depending on their position. On the upper jaw, there were premaxillary, maxillary, and pterygoid teeth. On the lower jaw, there were dentary teeth. In each jaw row, the pattern was generally 2 front premaxillary teeth, 12 to 16 upper maxillary teeth, 8 to 16 pterygoid teeth, and 14 to 17 lower dentary teeth. Most teeth were similar in size and shape, except the pterygoid teeth, which were smaller. Tooth counts varied slightly between species and individuals. M. hoffmanni, for example, had 14 to 16 maxillary teeth, 14 to 15 dentary teeth, and 8 pterygoid teeth. M. missouriensis had 14 to 15 maxillary teeth, 14 to 15 dentary teeth, and 8 to 9 pterygoid teeth. M. conodon had 14 to 15 maxillary teeth, 16 to 17 dentary teeth, and 8 pterygoid teeth. M. lemonieri had 15 maxillary teeth, 14 to 17 dentary teeth, and 11 to 12 pterygoid teeth. M. bogei had 12 to 13 maxillary teeth, 14 to 16 dentary teeth, and 6 or more pterygoid teeth. One unusual specimen from North Dakota had 16 pterygoid teeth, far more than normal. The teeth were firmly anchored in the jawbones and were continually replaced throughout life. Each new tooth developed inside the root of the old tooth and gradually pushed it out. Studies on a M. hoffmanni tooth showed that the cells forming dentin, called odontoblasts, added material at a rate of 10.9 micrometers per day. By examining daily growth lines in the dentin, scientists estimated that it took the odontoblasts around 511 days to form, and the dentin itself about 233 days to reach its final size. One of the most complete Mosasaurus skeletons ever discovered, catalogued as SDSM 452, shows an impressive representation of its spine. This individual had 7 neck vertebrae, 38 vertebrae along its back, which include both thoracic and lumbar bones, and 8 front tail vertebrae without hemal arches, followed by 68 caudal vertebrae extending down the tail. Every species of Mosasaurus is known to have 7 neck vertebrae, but the total number of vertebrae in the back and tail differs across species. Partial skeletons of species such as Mosasaurus conodon, Mosasaurus hoffmanni, and Mosasaurus missouriensis suggest slightly different counts. M. conodon may have had up to 36 dorsal vertebrae and 9 pygal vertebrae. M. hoffmanni likely had up to 32 dorsal vertebrae and 10 pygal vertebrae, and M. missouriensis is estimated to have had about 33 dorsal vertebrae, 11 pygal vertebrae, and at least 79 tail vertebrae. Among them, Mosasaurus lemonieri had the most, with roughly 40 dorsal vertebrae, 22 pygal vertebrae, and 90 caudal vertebrae. Compared with other mosasaurs, Mosasaurus had a uniquely deep rib cage, forming almost a perfect semicircle that gave it a barrel-shaped chest. Unlike many reptiles whose ribs are fused, the ribs of Mosasaurus were likely connected to the sternum by flexible cartilage, allowing it to breathe more effectively and compress its body while diving into deeper waters. The texture of its bones is very similar to modern whales, showing that Mosasaurus had advanced adaptations for a fully aquatic life, including the ability to maintain neutral buoyancy, just like cetaceans. The tail of Mosasaurus also shows remarkable adaptations for swimming. Similar to close relatives like Prognathodon, soft tissue evidence suggests it had a 2-lobed tail. The tailbones gradually shortened near the middle and then lengthened toward the end, which would have provided stiffness near the center for stability and flexibility further back for propulsion. Like many advanced mosasaurs, the tail bent slightly downward as it approached the center, though this angle was small. Large hemal arches ran along the underside of each tail vertebra and bent near the middle of the tail, a feature not seen in other marine reptiles such as ichthyosaurs. These adaptations suggest Mosasaurus had a massive, powerful paddle-like tail fin that could deliver strong thrusts for rapid swimming. The forelimbs of Mosasaurus were wide and sturdy. The shoulder blade and upper arm bone were fan-shaped, broader than they were tall, while the lower arm bones, the radius and ulna, were short, with the radius being larger than the ulna. The hip bone, or ilium, was long and slender. In M. missouriensis, it measured roughly 1.5 times the length of the femur. The femur itself was about twice as long as it was wide, ending in 2 distinct joint surfaces, one connecting to the ilium and the other to the paddle bones, forming an angle of about 120 degrees. The paddles contained 5 sets of finger bones, with the 5th set shorter and offset. These compressed, streamlined paddles were well suited for fast swimming, similar to the paddle structure of Platysaurus. In the hind limbs, the paddles were supported by 4 sets of digits. Mosasaurus was likely an active predator, hunting a wide range of marine life. Its diet probably included bony fish, sharks, cephalopods, birds, and even other marine reptiles such as smaller mosasaurs and turtles. It likely did not scavenge because its sense of smell was poor. Mosasaurus was one of the largest marine predators of its time, and its large, sharp teeth suggest that bigger individuals could take on nearly any prey. Evidence of aggressive feeding behavior comes from deep tooth marks on the armored shells of giant sea turtles like Liopluridon hoffmanni, as well as fossils showing healed jaw fractures in M. hoffmanni, indicating encounters with large and struggling prey. It likely hunted near the ocean surface as an ambush predator, using its large eyes adapted for spotting prey in 2 dimensions, though chemical and structural evidence from M. Lemonnieri and M. Chronosaurus suggests some species could hunt in deeper waters. Studies of carbon isotopes in M. hoffmanni fossils show extremely low D13C values, the lowest recorded among all mosasaurs for the largest individuals. Low D13C is associated with higher trophic levels, often reflecting diets rich in lipid-heavy prey like sea turtles and large marine reptiles, confirming M. hoffmanni as an apex predator. Analysis of tooth wear also shows that it had a generalist diet, as did M. missouriensis. Only 2 Mosasaurus fossils have been found with stomach contents. The first is a well-preserved partial skeleton of a small M. missouriensis, about 75 million years old, which contained pieces of a 1-meter-long fish, much longer than the mosasaur's skull, which measured 66 centimeters. This shows that M. missouriensis could eat prey larger than its head by dismembering it into smaller pieces. The second, nicknamed Lars, is a subadult M. hoffmanni skeleton containing acid-corroded bones of a juvenile turtle and other unidentified animals, along with possible bird bones, suggesting a varied diet. Interestingly, Mosasaurus may have taught its young to hunt. A fossil of a nautiloid, Argonautilus catarrhini, shows bite marks from 2 mosasaurs, likely a juvenile and an adult, indicating that one may have been learning to hunt from the other. The bite positions suggest the nautiloid was already incapacitated or dead, possibly serving as a practice target for teaching. Differences in tooth spacing indicate the bites came from 2 different individuals. By the end of the Cretaceous period, mosasaurs had reached the peak of their evolution, but their extinction came suddenly. During the late Maastrichtian age, global sea levels fell, draining nutrient-rich seas and reducing habitats for Mosasaurus. The genus adapted by moving into more open waters. The last fossils, including M. hoffmanni and others, appear up to the Cretaceous-Paleogene boundary, where the genus ultimately went extinct along with the non-avian dinosaurs. Mosasaurus fossils have been found less than 15 meters below this boundary in the Maastricht Formation, the Davatlar Formation in Turkey, the Jaguel Formation in Argentina, Stevens Klint in Denmark, Seymour Island, and Missouri. Some M. hoffmanni fossils occur directly at the boundary in southeastern Missouri, within a layer likely formed by a massive tsunami caused by the Chicxulub asteroid impact. These fossils show post-mortem fractures, suggesting catastrophic forces. The asteroid impact also blocked sunlight, causing a collapse of marine food webs, meaning any surviving Mosasaurus in deeper waters eventually starved. An unusual occurrence of Mosasaurus fossils appears in the Hornerstown Formation, normally dated to the Paleocene-Danian age just after the Maastrichtian. Fossils there are mixed with sharks, bony fish, and ammonites. This does not mean Mosasaurus survived the extinction. The fossils may have been eroded from older Cretaceous deposits and redeposited, a phenomenon supported by worn and abraded bones. Some remains were better preserved, suggesting a combination of reworking, sediment lag, and redeposition events caused by ancient tsunamis. Thalattoarchon is an extraordinary genus of enormous meat-eating ichthyosaurs that swam the oceans of what is now North America during the Middle Triassic period. It is known from only one species, named Thalattoarchon saurophagus. This remarkable marine predator was first described by scientists in the year 2013, based on a single, incomplete skeleton that was uncovered in the rugged landscapes of Nevada. Its genus name, Thalattoarchon, comes from ancient Greek and means ruler of the seas, a fitting title for an animal that dominated its marine environment. The species name, saurophagus, also derives from ancient Greek, translating to lizard eater, highlighting its fearsome carnivorous appetite. Like all ichthyosaurs, Thalattoarchon had 4 flippers that functioned like paddles and a fin at the end of its tail for steering. Despite having a long and slender body, it had a relatively huge head and a long, straight tail. This marine giant is estimated to have been between 8 and 9 meters long, or about 26 to 30 feet, making it one of the largest predators of its time. Its jaws were filled with enormous blade-like teeth, each up to 12 centimeters long, or nearly 4¾ inches, with sharp cutting edges that could slice through the flesh of its prey. Although the fossil record is incomplete, scientists estimate that Thalattoarchon had at least 60 vertebrae in the section of its spine in front of the hips. The exact place of Thalattoarchon in the ichthyosaur family tree is still debated. Some researchers classify it within a more advanced group called Meriamosauria, while others place it in the older, more primitive family Symbospondylidea. Its sharp, slicing teeth suggest it preyed not only on fish, but also on other marine reptiles, securing its position at the very top of the food chain. In this way, its hunting habits are often compared to modern orcas, which also dominate their aquatic habitats. Thalattoarchon is known from the Favre Formation, a coastal oceanic region that existed around 244.6 million years ago, during the early part of the late Anisian stage of the Middle Triassic. This environment teemed with life, including many other ichthyosaurs, which likely evolved different feeding strategies to avoid competing with one another. The only known Thalattoarchon specimen was discovered in the year 1997 by the paleontologist Jim Holstein during a field expedition in the Augusta Mountains of Nevada. Complete excavation of the fossils was made possible in the year 2008 with support from the National Geographic Society after 3 weeks of careful work. The bones were removed from the site using a helicopter and a truck, ensuring their safe transport to a research facility. The fossils came from the Taylori zone of the Fossil Hill member in the Favre Formation, dating to roughly 244 million years ago. Catalogued as FMNH PR 3032, the specimen includes most of the skull and the axial skeleton, along with parts of the pelvic girdle and hind flippers. It was formally described in the year 2013 by a team of scientists including Nadia B. Frobisch, Jörg Frobisch, P. Martin Sander, Lars Schmitz, and Olivier Riepel, and officially named Thalattoarchon saurophagus in the journal Proceedings of the National Academy of Sciences. Thalattoarchon was a massive creature, estimated at over 8 meters 6 decimeters long, or roughly 28 feet, though later assessments by Darren Neisch in 2023 suggested it may have reached 9 meters or 30 feet. Its body was long and slender, with a remarkably large head, which measured about 1 meter 2 decimeters, or nearly 4 feet, long. Unlike later ichthyosaurs from the Jurassic and Cretaceous periods, it had a long but poorly developed tail fin rather than the two-lobed tail seen in its descendants. Its skull, while shorter than some other ichthyosaurs, was robust, capable of delivering powerful bites to its prey. The preserved skull shows that the front snout and the tip of the lower jaw are missing, but the rest remains intact, allowing scientists to study its overall shape. The eye sockets were long, reaching 29 centimeters, or about 11 inches, and contained scleral rings. The large oval openings behind the eyes, called superior temporal fenestrae, are shaped similarly to those of the ichthyosaur Shastasaurus. Its upper jaw, or maxilla, extended far below the eyes and carried large teeth all the way to the back. The nasal bones were broad and connected with the bones behind the eyes, while the frontal and parietal bones formed parts of the openings on the skull roof. Small crests and plates on the skull provided attachment points for muscles and structural support. Inside the mouth, the pterygoid bones dominated the palate, while the lower jaw extended back alongside the upper jaw, though the very last teeth were missing. The largest preserved tooth measured 12 centimeters, with a crown of 5 centimeters, or about 2 inches, and each tooth had 2 sharp cutting edges. This distinctive dentition is one of the key features of Thalattoarchon, setting it apart from even closely related genera like Himalayasaurus, which had grooves along its teeth. The vertebrae tell a story of strength and flexibility. Though the total number is unknown, the presacral spine alone likely had at least 60 vertebrae. The front dorsal vertebrae were nearly round, measuring 10 centimeters in diameter and 6 centimeters in length, while the middle dorsal vertebrae were slightly larger at 12 centimeters in diameter. The neural spines extended taller than the vertebrae themselves, and the ribs varied from single-headed in the front to double-headed further back, as seen in some primitive ichthyosaurs. The tail vertebrae were flattened side to side, twice as tall as they were wide, and the tail appeared straight, without the downward curve that is typical of later ichthyosaurs. Only a few bones of the pelvic girdle and hind limbs survived, with the right ilium being the only fully preserved element. The femur was broad and flattened, with an expanded lower end, and the other hind limb bones were proportionally small compared to the animal's massive body. Overall, the hind limbs were tiny relative to the length of the spine, with the femur roughly twice the height of the front tail vertebrae. Ichthyosaurs, including the giant predator Thalattoarchon, were perfectly built for life in the oceans. They spent their entire lives swimming in water, and their bones were less dense than those of land animals, making movement in the water easier. Still, like all air-breathing reptiles, ichthyosaurs needed to surface regularly to breathe. These creatures were active hunters with fast metabolisms, which allowed them to keep their body temperatures steady even in cooler waters. Their large eyes hint that sharp vision was one of their most important senses, helping them spot prey in the dim light of ancient seas. Thalattoarchon and other ichthyosaurs with intermediate body shapes likely swam in a style called anguilliform, or subcarangiform locomotion, which meant they moved by sending wave-like motions through their entire long, flexible bodies. Their tails were long and gently curved rather than sharply bent, which allowed the whole body to ripple as they propelled themselves forward. This is different from later, more streamlined ichthyosaurs, whose swimming relied mostly on their powerful tails, while their bodies remained relatively rigid. Thalattoarchon stood out as a true apex predator. Its large, strong head and blade-like double-edged teeth were perfectly suited for slicing through flesh. Fossils from the Favre Formation show that the seas where it lived were filled with other marine reptiles, which would have made regular meals for such a top predator. Its role in the ecosystem would have been similar to modern killer whales, hunting large prey, sometimes possibly even animals bigger than itself, using its sharp teeth to take them down. However, it probably avoided the largest ichthyosaurs like Symbospondylus, focusing instead on medium-sized marine reptiles or younger, smaller individuals. In 2021, a team led by Sander proposed that if Thalattoarchon ever targeted large ichthyosaurs, such as Symbospondylus, it might have done so in groups, a kind of pack hunting. Yet, no fossil evidence has been found to confirm this behavior. More likely, Thalattoarchon fed on smaller prey, whether alive or already dead, a strategy similar to that of the modern great white shark. Its teeth and hunting style suggest it rarely, if ever, ate ammonites, squid, or fish. All these traits, combined with the age of its fossils, indicate that Thalattoarchon was the oldest known marine megapredator among four-limbed animals. It lived at a time when the oceans were slowly recovering from the massive Permian-Triassic extinction, which had wiped out much of life on Earth. This means that the rise of large, powerful ichthyosaurs like Thalattoarchon may have played a key role in the rebirth of marine ecosystems during this period.